In this lecture, I will explain the inner working of Bitcoin. I assume that you already know the basics of blockchain. If not, please check out my previous videos right here. In order to clearly explain Bitcoin, I will explain 4 different versions. Each version will build upon the last version. And the last version is closest to the actual working of Bitcoin. So let's start. Let's start with the version number 1. Version number 1 assumes that everyone is trustworthy. It is the simplest version. In this version, assume that Alice wishes to send around $18,000 to Bob. $18,000 is approximately equal to 2 Bitcoins. So to accomplish this, Alice will create a transaction, and the transaction will have amount 2 Bitcoins, receiver Bob, and the sender Alice. Now Alice will submit this transaction to the Bitcoin community. The Bitcoin community comprises of multiple entities called nodes. These nodes are either maintaining full or partial blockchain. This is the key difference of Bitcoin as compared to traditional currencies. In traditional currencies, there is a central bank and the government which are maintaining and regulating their currency. In contrast, in case of Bitcoin, we have a public ledger, and this public ledger is distributed because it is not maintained by a single entity, but there are thousands of nodes. Each node has its own copy of the blockchain. In this figure, I have shown 4 nodes. In reality, we have hundreds of nodes, but I've only shown 4 of them. Each node has its own copy of blockchain. So node 1 has this copy of blockchain, and node 3 has this copy of blockchain. Similarly, each node will be aware of multiple transactions that are not yet made part of the blockchain. For instance, node 1 is aware of 4 transactions, and node 3 is aware of 3 such transactions. Note that due to the faulty nature of internet, the view of each node might be different from the other node. For example, node 1 is not aware of the green transaction, whereas node 4 is not aware of black transaction. Each node will try to group these transactions in a block and then add that block in the blockchain. These nodes are competing against each other. It is because the first node that will extend the blockchain will be rewarded with 12.5 Bitcoins. In this example, assume that node 1 is the fastest and is able to extend the blockchain before other nodes with a new block, and that block and the node 1 has included 2 transactions. One is a blue transaction and other one is a pink transaction. In order to claim the reward, node 1 will broadcast the change in the blockchain to the other nodes. The other nodes will validate the change. If the change is legal, and if the change is legal, then other node will also update their blockchain with a new block. Now you can see that other nodes have also updated their blockchain with the new block based upon the information received from the node number 1. In our example, we have assumed that each block can contain only 2 transactions, but in reality a block can contain hundreds of transactions. So the question can be asked that why the node 1 has chosen these 2 pink and blue transactions. It is because each transaction may optionally has a transaction fee associated with it, and that fees also goes to the miner. In our case, the fees associated with the blue and pink node was maximum as compared to the other transaction. Therefore, the node number 1 has chosen these 2 transactions to maximize its profit. Now all the nodes will remove blue and pink transaction from their pending transaction list. and the node 1 will be rewarded 12.5 Bitcoin for the mining, and also 0.1 and 0.3 Bitcoins as a transaction fees. In total, the node 1 will get 12.9 BTC as profit. This process will continue. In the meantime, more transactions might arrive, and with the additional transaction and the remaining transactions in each node pending list, each node will compete with other nodes to extend the blockchain and maximize its reward. And this concludes version number 1 of Bitcoin. Now you somewhat know how Bitcoin works. But version number 1 has lots of drawbacks. Two of the key drawbacks is as follows. Number 1, anybody can pretend to be a receiver. Anybody can pretend to be a sender. So anybody can pretend to be Alice. Anybody can pretend to be Bob. And let's improve these two drawbacks in the version number 2. So welcome to the version number 2 of Bitcoin. In the version number 2, we have to ensure that this transaction is generated by Alice and Alice only. And this transaction is received by Bob and the Bob only. Oscar cannot generate this transaction, and Oscar cannot receive this transaction. So what we're going to do is that instead of writing receiver as Bob, we will write here public key of Bob. So we don't write the Bob here, but the public key of Bob. It has two advantages. Number 1, that now Bob has privacy. Because nobody knows that this public key belongs to Bob, and that is why nobody knows that this transaction will be received by Bob, and now Bob has privacy. Second advantage of writing public key is that this transaction is locked, and that lock can only be opened by the private key of Bob. So we have locked this transaction, locked for Bob, and in order to use this transaction, Bob has to sign this transaction using his private key. Only after signing this transaction, Bob will be able to use this transaction. We also have to ensure that sender is indeed Alice and not a hacker Oscar pretending to be Alice. Furthermore, we also have to protect the identity of the sender. In order to accomplish this, instead of writing here Alice, we will write here digit signatures of Alice. So now this transaction is between two public keys, public key of the receiver and the public key that correspond to the digit signatures of the sender. By signing the transaction, Alice has also protected the content of whole transaction. Now if anybody changes the receiver public key or the amount, then the signature will become invalid. So second version is a significant improvement over the first version, because in the second version the identity of the sender and the receiver are well protected, and in second version nobody can change the content of a transaction. But second version still has lots of disadvantages, and some of these disadvantages will be improved upon in the third version. So far we have no check on the rate of transactions. It is possible to add a new block every millisecond in the blockchain. Thus we will be mining 1 million bitcoins every minute, and this inflation has potential to make the valuation of Bitcoin worthless. Secondly, so far we have no protection against dishonest miners. Although a miner cannot change content of a transaction, because each transaction is protected by the digit signatures of the sender, however, a miner can still change the content of a block. Consider a scenario. We have a long blockchain, and this block has two transactions, blue and pink. assume that the node number 1 is a dishonest node. So node number 1 removes the red transaction and replaces it with a yellow transaction. In order to achieve this, node number 1 has to recompute Merkle tree in this node and in this block, and node number 1 has to recompute hashes of all the blocks that are succeeding this block. As hashes can be computed quickly, therefore it is not difficult for node number 1 to recompute all the hashes and change the blockchain. To solve both of these problems, that is excessive inflation and dishonest miners, Bitcoin uses a Hashcash based proof of work system. Let me first clear the board to demonstrate how Bitcoin's proof of work functions. So let's say that I'm a miner and I want to add a new block in the blockchain. So first I will add transaction in the body of the block. Assume that I add a black transaction and a green transaction, and then I will compute the Merkle tree of this transaction, and based upon the Merkle tree I will add Merkle root in the header. So I add Merkle root in the header. And I will also compute hash of the previous block, and I will add hash of that block here. And that means that I'm basically establishing this link with the previous block. However, this block is not yet a valid block and thus cannot be advertised to the other nodes of the community. To convert it into a valid block, I first have to solve a hash puzzle known as Hashcash. The Hashcash puzzle says that the hash of the block being added in the blockchain must have some preceding zeros followed by a random number. So if I compute hash of this block, I might not have some preceding number of zeros, I might have only a random number. So here comes another field in the header known as nuns. Nuns is a counter that I can use to change the content of the block and then recompute hash again and again. So what I have to do is that I will select nuns equals to 1, because nuns equal to 0 was all random numbers, no preceding zeros. So I have selected nuns is equal to 1 and then I recompute the hash. If my new block, header of the new block has some preceding number of zeros, then I'm done. Otherwise, I will have to increment nuns once again, make it maybe 2, and then recompute the hash of the header of the block. If the new hash of the header has some preceding number of zeros, then I am done. Otherwise, I have to increment the nuns once again. So I have to continue to increment the nuns until the header hash is a preceding number of zeros and then some random number. So one question can be asked that how we know how many zeros should precede a random number, and it depends upon the difficulty target set by the Bitcoin software based upon how frequently blocks are being added in the blockchain. The difficulty target is set in a manner so that on average a new block can be added in the blockchain after every 10 minutes. Assume that in my case nuns came out to be 1 trillion, and then the block the header hash become valid because it has a required number preceding zeros followed by a random number, and now I can add this block in the blockchain because this is a valid block and the community will accept that block. Now adding a block in the blockchain requires gigantic amount of work, and if a hacker wants to change a block deep down in the blockchain, then he has to recompute hashes of all the succeeding blocks. That means changing a block deep down in the blockchain is even much more difficult. Well, that's it for today. I hope that you have learned something new. See you next time.